And today, what I want to talk about is Python and give you my perspective on why I think Python is such a powerful language, why I think it matters in the world of embedded development, working with microcontrollers, single board computers, all that fun hardware stuff. I'll start with a bit of history, talk about some of the flavors of Python available on devices, and then I'll mix in a few demos along the way. But first, let me start by stating why I think Python matters. Whether you are an embedded developer used to C or C++, or a software engineer potentially interested in working in this space, which is where I came from, and I think that's probably where most of us are as well. And it starts with complexity, frankly. A lot of the software in the hardware in the hardware world revolves around how we can actually deliver products, how we actually get things into production, how we get things across the finish line. And you know this well as a developer. If you're working on a site or an app, there are a number of things that can trip you up or slow you down. And this is absolutely true in the hardware world as well, where the existence of atoms adds even more complexity beyond the bits and bytes that we already have to deal with as software developers. And when I think about complexity, I think about a quote from Ray Ozzie, the CEO and founder of my company, Blues Wireless. And that quote is, "Complexity kills." And I'm guessing that many of you have heard that one before or heard something like it because it's something that Ray said many years ago in his software days before starting Blues Wireless. And in the embedded world, part of the complexity lies in languages and tool chains, where there hasn't really been as much innovation as there has been in the desktop computing world. And I could take this moment and start criticizing the C and C++ languages or making some sort of joke at their expense. I'm not going to do that. But I will say that C and C++ aren't for everyone, and the learning curve for these languages is quite steep. In fact, I'm guessing that there are some of you in the room that experienced C or C++ at some point in your career and decided that you don't ever want to go there again. That's a common refrain that I hear a lot of times. But when it comes to considering programming languages and embedded systems, we should consider that businesses around the world are set to deploy billions more embedded and connected devices in the coming years. And these devices need developers, many, many more developers than those that are working professionally with C and C++ today. A lot of the explosion that we've seen of opportunity around software development because of desktop and cloud computing and mobile is still there and even broader and larger for the world of IoT, where there are billions upon billions and some project even trillions of devices in our future. So the question then becomes, what are our options as an industry if we want to enable the next 50 billion embedded devices? Do we insist that C and C++ are the only path through the door, or do we consider another approach? Now, if you are a C or C++ aficionado, you might tell me that according to the TOB index for August of 2021, C is still the most popular language, with C++ at number 4. And you'd be right. Although it is important to note that Python did move solidly into the number 2 slot over the last year. There's no doubt that C is still a very popular language in terms of what people are using for the apps that they're building today. But what if we looked at the data a different way? What if instead we looked at not what people are actively using, not what we're all using professionally today, but what people are learning and hope to use in the future? Because I believe that's the best indicator of where the long-term opportunity lies. And here, the data are pretty clear. Based on an analysis of people searching for language tutorials, Python is the clear favorite, right? The point of this chart is to say that people that are looking, people that want to learn something new are by and large choosing Python as the language that they want to learn. And there's a lot of reasons for this. Python is already a language that can and is being used in a ton of different areas, from web development to machine learning, data visualization, game development, and more. And it's also becoming the most popular language for introducing coding to students, whether they're kids or adults. If you're new to programming, by and large, people are choosing Python as the entry point to go in. So if we in the IoT and the embedded world are looking to pin down the next generation of what devices will be built in and how they will be built and what they will run, I think we can look no further than Python. Now, before I get into the specifics of what that means on individual devices, I thought it might be helpful to share a few of the advantages of Python on devices as I see it. If you're already a fan of Python, these might not be news to you, but if it's a language that you know about, you've dabbled in, you're sort of generally interested in or not, maybe these things will be interesting. The first, and this is probably my favorite, is that there's no compilation in Python. Python is an interpreted language, whether you're working with it on a desktop or whether you're working with it in a microcontroller. You don't have to worry about setting up crazy compiler tool chains in order to use the language. And for somebody that spends a lot of their time day in and day out working with embedded devices, the saving of the compilation step is actually pretty nice. Those of you that work in the web and work in desktop computing environments and things like that are lucky, because you don't have the same experience of waiting sometimes a long time for a binary to compile before it goes on an embedded device. The second thing, and this is probably my favorite, is a live REPL, live debugging. So if you've ever worked with Python before, you're familiar with this. You've experienced the use of the REPL. And I'm actually excited to share that this is something that is available on microcontrollers, on embedded devices as well. And we'll look at that in a little bit. But this ability to actually jump into a running device or a running program and inspect how it's going, inspect what it's doing without having to get into the complexity of step-based debugging is really nice. The third advantage is machine learning on single board computers and on microcontrollers. We did a workshop on machine learning in the IoT in the cloud the last couple of days, and this is something that's near and dear to me. I'm a big fan of machine learning in general. It's an area I've spent a lot of time in the last several years, but it's also an area that I think there's a lot of power between AI and ML and the IoT, right? And so having the ability to actually perform inferencing, to actually capture sensor data and evaluate that in real time in Python is another area where there's a lot of work and a lot of interest happening. And then finally, it's just Python. I say this as someone who I spent most of my career as a web developer. I started way back in the late 90s working on ASP Classic web applications, was a .NET developer for many, many years. I have dabbled in a ton of different languages, but Python has become far and above my favorite. I enjoy the expressivity of it. I enjoy using the language day in and day out. It's actually a lot of fun. I don't actually mind significant white space, believe it or not. I always thought that I would, but I don't. So now let's talk a bit about Python variants and when you'd want to consider each for an application, because there's actually different flavors of Python or subsets of Python depending on the kinds of devices that you might be using. The first one is CPython, aka the OG Python. Now this is the original C-based Python, C-based Porto Python. This is the one that you can use on single board computers. If you're using a Raspberry Pi, you're using an NVIDIA Jetson, you're using really any class of device that has its ability to run its own Linux, but it's still considered to be an embedded system, you can run full-on Python on those devices. The only caveat to this is that sometimes some Linux distributions, I think this is becoming less and less the case, but some Linux distributions still do default to Python 2.7, which nobody's supposed to be using anymore. So I don't have a Raspberry Pi with me. I will be able to show you the actual other devices, but let me actually very briefly show you a demo of what or show you some example code of what it looks like to work with Python in a Raspberry Pi environment. So if you've ever worked with Python before, even if you haven't, I think most of the code here will generally make sense. You start with importing a couple of the dependencies that you want. What typically happens when you're using Python on a Raspberry Pi in an IoT system, you're also working with some sort of sensor, some sort of device that is reading something about the environment for you. So in this case, what I have, and you'll see this in the other boards as well, is something called an Adafruit BME 680. It's a Bosch temperature, humidity, pressure, and gas sensor. That's all it is. It's a tiny little device that measures that environmental information for me. So there's a library that I can use that helps me work with that device. I import a couple of other libraries that actually allow me to access one of the buses that allows for communication between a board and a set of sensors. And so I import that library and then I start the sensor. And that is effectively, if you're used to Arduino programming or even if you're used to doing other sorts of C-based applications, that is all of my setup that goes on the top. And the bottom, the while true in the Python world is my loop. This is what's running over and over again as my program executes once I actually put that software on there. So in here, all I'm doing is I'm pulling out the temperature and humidity. I'm printing that out to some sort of console, and I'm going to sleep for 15 seconds. It's a very dead simple program, and that is literally as easy as it is to use Python on a single board computer like the Raspberry Pi. You'll get to see that again you'll see actually as we walk from one of these to the next, how similar Python looks, even though there are variants of these things. Now the next is called MicroPython. This is an implementation of Python 3 that was optimized for running on microcontrollers. So it's purpose built for running on tiny constrained devices. I mean, this is one of the important things if you have not ever done microcontroller development before. Constraints are the rule of the day. Even as devices are getting more powerful, even as they're able to do more, we still have to be very flash and RAM conscious when we're building applications. It's not all that dissimilar from desktop development in the 80s and probably even the early 90s. MicroPython has great support for running on the ESP32 and Raspberry Pi Pico. And as you'll see in just a second, it's actually a language that is very, very similar to what you just saw in the last example. So I'm going to actually mirror my screen here so I'm not looking at the screen behind me. And I'm going to actually, for a second here, show you what one of these things looks like through the magic of QuickTime on my iPhone. So we'll see how this goes. And I have, is it actually going to work? Do I have to unlock first? Get ready, you're going to get a close-up of my face for a second. Sorry about that. I always love how these things demo so well 5 minutes before the talk starts, and then they don't work again afterwards. Super. New movie recording. My God. Thanks for nothing, Apple. Thank you, Rob. QuickTime. Shame on me for unplugging anything. All right, so new movie recording. Here we go. I hope that you are impressed by what I'm about to show you if I actually get this to work. Never mind. Never mind. I'm not even going to bother trying. Yes, I am. I'm going to try one more time. All right. I know half the reason that y'all come here is to watch presenters fail at the demos, right? I know it. That's why I go to conferences. All right. So I'm going to show this from a distance, and y'all are welcome to come and check these out after the fact if you want to see it closely. But this is a board called the Raspberry Pi Pico. It runs a tiny little microcontroller. It is created by the Raspberry Pi Foundation, but it is not a Raspberry Pi single board computer. It's a cheaper device that's a couple of bucks, and it is connected to this device I was mentioning earlier, this Adafruit BME 680, this Bosch temperature, humidity, pressure, and gas sensor. And it is actually connected. I'm using an IDE. You can use MicroPython and CircuitPython inside of editors like Visual Studio Code, but there's a couple of purpose-built IDEs out there that are actually kind of fun to work with as well. And one of these is called Thani. I think that's how you pronounce it. And that is what I have open right now. And I'm actually connected over the shell. I have a shell connected into my Raspberry Pi Pico so that I can do a couple of interesting things here. Let's see. So one of the things that I can do is I can do an import. So again, I mentioned earlier, one of my favorite things about working with Python on microcontrollers is this idea of live debugging. So I have MicroPython running on this device. I have a shell open, and I'm actually able to inspect the running program while I'm working with it. And this is, if you've ever done embedded development, this is just stinking amazing. So I can actually use basic Python commands. The dir command basically gives me a listing of all of the attributes, properties, methods on a device. So again, running this in real time, it's telling me these are the methods and properties available on the pin object. I can do interesting things using other built-in MicroPython libraries like import OS. So you see there's some standard ports of basic what you see full-on C Python libraries like OS, things like that. You'll see these in MicroPython distributions as well. Actually, don't need to do print. And I'll do os.uname, and this will give me information about the device. So I can see a tuple of, hey, I'm running on the Raspberry Pi Pico with the RP2040. Again, this is real time. I'm working with the device. Now, I had hoped, we'll see, I'll just hang this off of the edge here, and hopefully it'll actually work. I was going to show you the LED on this thing light up. I'll just hold it up each time. So what I can do next is set variables. So the LED, the pin on the on the Raspberry Pi Pico that's connected to the onboard LED is pin number 25. So I can set a variable for that. And then I can create an LED object and bringing that pin library back in that I just imported, LED pin. And you'll notice that on the attributes I have in, out, a few different things that I can do there. So I'm going to set this as pin.out. Basically means that I'm going to write to the pin. Let me fix my misspelling. And now what I can do, and you'll notice as well with the LED object, there's a few other things like high, init, IRQ, low, toggle, value. I can do LED.value. And I'll do LED.value, and for those of you, hopefully everybody can see this, but if I do LED.value.1, hit enter, the LED on the top of the board will actually light up. If I do LED.value.0, it'll turn back off. Now, I have others like LED toggle that'll turn the light back on. If I run it again, it'll turn it back off. This is actually really, really freaking amazing. If you have worked with embedded devices with microcontrollers before, this ability to real time change the device, to update its state, to interact with it without compiling anything. I'm not recompiling anything. It's handling this all on the fly with MicroPython, and that is really, really interesting. So in the example that I have above, you'll notice some code that is pretty similar to what I shared with the Raspberry Pi. So slightly different. I'm importing UTime. There's a couple of libraries that MicroPython has ported over from full-on C Python that have the U in front of them, like for micro. And I'm importing the machine object like you saw me do earlier. I'm importing an Adafruit BME 680 library, and the same as I showed you before, turning the pin off and on as I read that value and print it out. So in order for me to run this now, all I need to do is basically tell Thani to run the current script, and there you go. It connects to the device. It's 24.6 degrees C in here. It was warmer when I came in an hour ago, so the temperature's come down, which is great. Humidity is 55, 48%, and it's running this every 5 seconds or so. And as it's doing so, it's very briefly blinking the LED on and off as it grabs a new reading. So that's MicroPython. Kind of cool, very, very easy to get started with. Now, next is CircuitPython. Now, CircuitPython is actually a fork of MicroPython that's focused on the ease of use and C Python compatibility. So one of the things that you'll see with these forks, and I know, many of us that get involved in open source software have different opinions about forks and whether or not they should happen, whether or not we should just sort of keep code happy and mainlined and all those good things. But it is a fork of MicroPython that was built around adding more compatibility into C Python. One of the things that early MicroPython development struggled with was a lot of the syntax was the same, but some of the libraries weren't the same. And so developers had a hard time really getting used to living in that world. This is a library that is actively supported and developed by a company called Adafruit. There's board support for Nordic, STMicroelectronics, and SAMD microcontrollers. There is a ton of different boards that work with CircuitPython, including a board from my company called the Swan. Now, the reason why I'm sharing the Swan is because we're going to demo this, but it's important because I also want to underscore in this part of the talk how powerful boards have gotten over the course of the last couple of years. When I first started doing embedded, when I first started getting into the maker world and getting into IoT development about 7-8 years ago, I was working with Arduinos, the Arduino Uno. The Arduino Uno, many of us have experienced and seen. It is a very, very low power, low memory, low flash, low RAM device. There's not much you can do with it There's a lot you can do with it, but when it comes to the kinds of modern things that people are trying to do with microcontrollers, there's not much to it. A lot of newer boards are offering a ton more RAM and flash. One example is this, is the Swan. It's a low power ARM Cortex M4 that's actually clocked at 120 megahertz. It's based on an ST microelectronics chip, and it comes with 2 megs of flash and 640K of RAM. Isn't it kind of funny? You remember those days in the early 90s where we'd be all impressed about like small amounts of flash and RAM, like megs and kilobytes? Well, in the embedded world, we're still excited about those small numbers, and that's okay. It's an MCU for the language polyglot. So this board actually supports C, C++, Arduino, and Python, and CircuitPython, and soon and MicroPython as well. And it's also an MCU that works really, really well in machine learning sets of use cases. So if you're somebody that's exploring the world of TinyML, this is actually a great board to work with. So, but enough of that. I actually want to demo that one now for you too. So very similar. Hey, look, here's just another microcontroller. I'm going to unplug the Raspberry Pi Pico here and unplug that same BME 680 sensor, and I'm going to unplug it here into the Swan. Oh no, maybe. All right. Now this board, there we go. All right. Go back over. Now what I'm going to do is I'm going to open up a new file, and actually I'm going to open up a file on my MicroPython, on my CircuitPython device. What's really cool about CircuitPython is when you plug a CircuitPython device into your computer, it actually registers as a drive. It uses a bootloader technology that was open sourced by Microsoft called UF2 that causes these microcontrollers to basically register as mass storage devices with a file system, which is really, really interesting. What that means is that the code that I write is literally just a matter of dragging and dropping that onto the device. I can include libraries and all that good stuff. So this is my file, code.py. There's not really all that much to it. In my interpreter, what I'm going to do is change this to CircuitPython generic. I'm going to update the port. Swan R5, click OK, and you'll see that I can run the device, and I'll just see hello world, and it'll be done. I can do the same things that I was doing before, import OS. This time if I print OS, and it's going to be os.name and not uname. Oh no, it is uname. Maybe so. Now different device, STM32L4, Swan R5. So same code, but I'm getting more information on the differences between these two devices. But I want to actually pull in the same code that I was using previously. And so I'm going to show you the slight variation here. This is actually even less different. I mean, there's a few minor differences between the MicroPython version of the same example and what we have here. But you'll notice that it's not syntactical. It's by and large just how libraries are referred and what standard imports are. In MicroPython, we imported utime. Here it's just called time. I have the same sort of library support. And I'm doing the same thing, measuring temperature and humidity and updating it every 15 seconds. So when I run that, I'll see now 25.9 degrees Celsius, 51% humidity. But one of the things that I sort of hinted at, but I haven't demoed explicitly yet, and this is sort of interesting, is the power of changing my application and redeploying it very quickly. Again, the no compilation not only gives me that ability to use a REPL inside of the device, but I can actually do more things. Like I can continue to update my program and to do more exciting things and save that quickly. So I'm going to add this temperature. The sensor actually also offers pressure. So I'm going to get the pressure value as well. I'm going to put that into a string here. And I'm going to print that as well. Oh, I don't need that. And there. So now all I need to do to actually apply this to the device and start it running the new program is just save it. And now I have the pressure as well as the temperature and humidity. It was that quick, no recompilation, literally just saved the file back down on the mass storage device and I was off to the races. Now, over the next little bit, I do want to spend a moment talking about the Internet of Things because this is an important piece here. It's great to be able to use Python on these devices. It's great to be able to program microcontrollers in this way. But the reason why we're interested in this as an industry and as developers is because we need to take that data and send it somewhere. We need remote monitoring. We need remote control. And I recognize that not every embedded application is not every embedded application is a connected application, but more and more of the devices that we're building rely on some kind of connectivity, even if it's something very close by like Bluetooth or NFC, some sort of connectivity between devices, whether we're talking about those two or Wi-Fi or LoRa or cellular. So there's good news for the Python world here because there's an increasing number of IoT vendors out there who are building for Python developers, not just insisting that you have to work with classic embedded languages in order to work with this space. And one such example is my company, Blues Wireless, and we tend to focus on providing device agnostic ways of connecting sensors and applications because we recognize that the reality is that most developers out there, most companies out there are looking to get their sensors, their information into their ultimate cloud applications, whether it's their own infrastructure or something like AWS, Azure, GCP, et cetera, right? And all of this middle piece here is a mess. When I mentioned that idea of complexity earlier, all of this stuff tends to be really difficult and time consuming for developers. And I think it has created this world where we tend not to start the projects that we really want to be able to build. And our product set starts with something called the Note Card, which is a low-power cellular and GPS device that has cellular IoT connectivity in over 135 countries, including pretty much all of Europe and Portugal. The device comes with 10 years and 500 megs of data baked into the cost of the device, so there's no monthly data plans, no activation fees. The price is on the tin, basically. So I come from a world where in the cellular IoT space, for years we have been used to this idea of, well, I got to buy a device, and then I have to buy a SIM card, and I have to pay $5 a month for a SIM card. A lot of the mobile operators out there price their cellular IoT devices like mini mobile data plans, where you got to sign up for something. And for me as a developer, that stopped me from starting and piloting and building out the ideas that I wanted to build. We don't have that problem. There's no activation fees, no ticking clock once you start your project. And instead of spending any time learning a labyrinth of AT commands, this is another piece. If you've ever done anything with cellular IoT, you might have learned that the language used to communicate with cellular modems is actually not all that different from the language used to communicate with 5600 baud modems 30 years ago. It hasn't changed that much. But instead of having to learn those commands, you can work with our 100% JSON API, which gives you everything from understanding the location of the device to understanding how to make it connect to the cloud, how you can actually get a status of data synchronization, to actually adding data to the device itself. So this is really powerful, which is why we like talking about it, because you can go from unboxing a device to sending any bit of data to the cloud in minutes. And every device includes secure keys for making a connection to a connection to our cloud services baked into the device. So there's no error-prone security problems, no error-prone key rotation or cloud provisioning. You literally just power it up, start sending it data, and it knows where to go in order to phone home. And in terms of where that goes, it goes to a service called notehub.io. This is our cloud service for ingesting your data before you need to actually send it to the place that it needs to go. And it's really designed to be a very thin middleware layer between the Note Card and cloud applications. So we make it really easy to route data out to a platform like Azure, AWS, GCP, anything like that. Because that's really the exciting part, right? The reason why we build connected applications is because we want something like this, right? We don't gather temperature and humidity data just because we want to see it streaming across a serial console. We actually want to see it in a dashboard of some kind. We want to build a connected asset tracker, some application that shows us how we manage things as they're online, or something that actually can monitor our heart rate and send that data up to the cloud. And that's the exciting part of all of this, and the things that we really like to enable developers to focus on. And so we have a lot of developers in our community that work with building things like water quality monitoring, air quality monitoring, and even monitoring analog systems. But enough of that. The whole reason that I brought all of that up is because we're not just device agnostic, but we actively support Python developers. We support C, C++, Python developers. We support .NET developers as well, those that are doing things with TinyCLR and other environments. And so we really try to meet developers where they are, and that includes having a complete SDK for our note card product that works out of the box with CPython, MicroPython, and CircuitPython, and allows you to speak to the devices. So for the last demo I'm going to show you today, I actually brought a note card with me with one of our boards called a note carrier, which allows you to very easily connect it to anything. And I'm just going to daisy chain this between my sensor and the ultimate Swan, the microcontroller itself. And that's going to add power to the device separately as well. It's not necessary, but for the sake of making sure that my demo actually works and everything behaves as desired, I'm going to do that and reset things. Okay. Let me go back into extending my display here. And here for this piece, what I'm going to walk you through very briefly is, I found a note card. Yep. I'm going to pull in this other set of code, and I'm going to save this onto my device. I'm going to walk you through it, and then I'll go through and save it. The only thing that I have to add to my existing application that's reading the temperature and humidity is a reference to that library. And one of the things that I think I kind of briefly mentioned, but maybe I skimmed over too quickly, is when I talked about this CircuitPython device registering as a mass storage device, not only does that give me access to a code file that I can very easily drag and drop, but it's that simple for me to just drop libraries onto the device as well. And so I have the Adafruit libraries that allow me to talk to the BME 680, but I also have the note card library that we have created in open source that allows me to talk directly to the note card, to send messages, to receive messages from the device, and all that good stuff. And that was as simple as just dragging that library into the lib folder on this, on my Swan device as well. So I mentioned earlier that we have this NoteHub cloud service. And so typically the way that the process starts is you'll create a project with one or more devices that you intend to send to it. And I have a lot because this is my day job. I do this all day, every day. But I've created one here for NDC Porto. I think that's the one that I used. Yeah. And so all that I need to do, every device or every project has something called a product UID. This is basically just a simple string. I mentioned earlier that when the note card wakes up, it knows where to go. It has its keys pre-provisioned. There's an eSIM on the device. It knows how to securely connect over the cell network into our VPN. But once it gets there, one of the things it needs to know is whose project does this go to? What is this device? Who's actually working with this and where? And so that product UID is that thing. That's that magic string that only I can have. It's unique because it's associated with my email address in the account and then the project name that I've given it. So that's the one thing that I've added there. And then I'm also adding an instance of my note card object, just connecting to it over I2C. Setting debug mode, which is going to actually output all of the commands as they come across. And then I'm doing a couple of things. I mentioned earlier here that we do this concept of 100% JSON-based API for talking to the device. So what you'll see in here is two different examples of that. The first is what we call hub.set. And this is just me telling the note card, this is this product. This is the project that this thing is actually associated with. And then I send that in a transaction. So that's, again, all my setup. And now I'm back in my loop. I got temperature, humidity, all that good stuff. Let me add back in what I was doing earlier of actually getting the pressure value as well. Sensor.pressure. format. And I'm going to add that in. And so this is then the second place where you'll see I'm doing something that is different. And that is I'm doing something called note.add. When you add data into the note card, it's referred to as a note, which is basically just some arbitrary piece of JSON that you're sending into the device to say like, hey, send this up to the cloud service. I'm going to need this somewhere later down the line. This is what that is. What I have in here to start with is temperature and humidity. And I'm going to add pressure to that as well. So that'll go along for the ride. And again, I send that and you'll see the response actually printed out. And then I go to sleep again for 15 seconds. So assume all of this is connected up correctly and it works. All again I need to do is actually just save it to run the current script. And what you'll see in this case is that these events will come streaming across. You'll see this was the same, this is what I ultimately sent to the note card. It's got some extra data in here, which we refer to as the user agent of the device. So we know where we can actually invest our time to support and improve different projects. And then that request executed successfully. And now I'm sending temperature and humidity. You'll see that note binding as it comes across. And then in order to actually see whether or not that showed up, I can load up my project. Now, inside of my project, I have the note card. This is my device. I can actually see where it is located based on cell tower access. So you'll see when you can actually inspect information about the device, get a little bit of information about its environment, recent JSON that's come across for it. So it can tell me it has the tower location. This is the name of the tower, the lat long of the device, all that good stuff. But events are where I can actually see the data that I've sent across. So you'll see temperature, humidity, and pressure coming across every 15 seconds or so. Now, from this point, it's really a simple matter of me setting up some third-party cloud service like Ubidots or Losant or DataCake, and then creating dashboards out the other end. But again, this is a simple matter of just adding some Python into my application, and I'm good to go. Right. So, where does that leave us? If this has been at all interesting and you're thinking about, I'd really love to check out Python, I'd really like to actually explore some of these microcontrollers, I highly recommend grabbing a Raspberry Pi Pico, getting a Swan, checking out. There's a ton of different devices that you can learn about on CircuitPython.org or MicroPython.org. The documentation for the Raspberry Pi Pico is at this URL as well. There's a ton of different places that you can go to learn more about working with these devices. And if by chance you're also interested in working with Blues Wireless, the note card, with the Swan, with any of our devices, you can learn more about what we do at dev.blues.io. So, any questions? Yeah. 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 No, CircuitPython is not further behind because that's a great question. The question is MicroPython and CircuitPython tend to lag a bit from CPython. You know, what's the status of where they are behind and whatnot. CircuitPython, because it's maintained by Adafruit, by that company and by a pretty active community, in addition to the fact that it was actually built with CPython compatibility in mind, they tend to stay as close. They tend to stay pretty close. I would say that CircuitPython right now is probably close to Python 3.6, which is not too terribly far off. I mean, there's a few cutting edge features that you might find lacking that are like, that's a bummer, but it's not too bad. I mean, it's better than writing C, right? Good question. Anybody else? Well, great. Well, if anybody has any questions after the fact, feel free to come up if you want to take a closer look at the devices. But appreciate you taking the time and have a great rest of the conference.